one of the most important projects in the microlensing subgroup. So
okay. So let me share my screen very quickly. Okay, so just to talk a little bit of an overview about what we've been doing. So just to recap the baseline, the survey strategy for Rubin way back in the day, originally it was intended to avoid the galactic plane entirely, largely because the science goals were originally driven by exoplanet science. So looking at this map of the sky, this is a much more up-to-date cadence map. The original map of the sky covered this large area in the middle in green, which is outside the galactic plane, which is the section you can see in blue. The blue color scheme represents the number of visits over the lifetime of the survey. So you can immediately see that the galactic plane was intended to receive fewer visits over the lifetime of the survey, which put some severe constraints on how much galactic science we were going to be able to do. So in the 2018 call for white papers on LST survey strategy, quite a few people, including the TVS Microlensing group, wrote in to say, hey, we're missing a lot of science here. There's an awful lot that we could do. And I've listed on this slide just a few of the proposals that were sent in. Microlensing was just one of the science cases that was highlighted as an area of science that would be neglected. Most of the stars in LSST would in fact be in that blue region and would have been neglected. So with that in mind, the LSST Survey Strategy Committee responded very well. They took all of this on board. They have said that they have been flexible about adjusting the survey strategy to put more visits to the galactic plane. And the end result of that was the phase 1 recommendations for survey strategy, which produced the survey cadence map that you can see printed on the slide. This region here is called the diamond, and it overlays the galactic bulge, which is around here. And it also includes the Magellanic Clouds, which are over here. So they adjusted the survey strategy to basically include those regions at a similar cadence that as would be received by the rest of the survey. Now, by microlensing standards, that cadence is still fairly low. It's once every few days in alternating colors. But we have still some flexibility in the overall survey strategy to adjust elements of this aspect of the survey, because it's almost orthogonal to the rest of the survey, the wide, far, steep survey in the outside the galactic plane. We can take the visits that we have been allocated and we can organize them almost how we like, provided it doesn't impact the rest of the survey too much, in order to maximize the science return overall, both for microlensing and everything else in the galactic plane. And so looking at this, this blob in the middle here, the diamond, I looked into whether or not it could be optimized on a more scientific way, because the way that this blob was arrived at was Lynn and Peter, who run the survey strategy simulations, basically said, well, people were asking for the bulge, which is around about here, and they wanted a section in the galactic plane, so that's around about here, and they draw a rough diamond. So the goal was to do to find out where the most important science regions were in a slightly more rigorous manner. So what we did was I looked at all of the white papers that had been submitted previously, and I took from them the regions of scientific interest that they had identified. And I overlaid each of those maps one on the other and came up with a combined map. which is a map of the entire galactic, of the entire visible sky. And it is quite fragmented. There are places of interest all across the galactic plane, right the way across the difference in the stars. So basically all of the areas where there are heavy stellar density. If you then use that map as effectively a vote, you look at the areas of the map which most people wanted to look at, you can use it to prioritize different regions of the sky. One thing that we noticed immediately was the end result was quite heavily concentrated to the central galactic bulge, which makes sense, it's high priority. But it doesn't give us much of an insight across the Milky Way. And the problem with that for microlensing is that we've spent quite a long time looking at the central galactic bulge. We don't know much about the rest of the galaxy, so we don't have a comparison population. So with that in mind, I added what I've called the pencil beam fields, which are single pointings of Rubin dotted along the regions of high stellar density across the Milky Way plane, with a view to basically increasing the priority of those fields so that they get included in the final combined map. Mm-hmm. So I submitted that, put together, submitted it to the SDOC, and the concern was that it's very fragmented. You end up with small patches that you want to observe right the way across the Milky Way, and they're disconnected patches, which is fine, except for the fact that in the scheduler, there's a slew time penalty because the telescope has to, the way it schedules observations, it has to jump from one field pointing to the next. Then if you spend a lot of time slewing from one field to another, it is extremely inefficient. It's a big telescope after all, it takes quite a long time to slew and settle. And so the end reason, the end result of that was that they asked me to find a way to centrally condense the fields into a more structured section. So I experimented a lot with some clusters so that then ended up with collated, seems like, with more contiguous field sections. And what I've plotted here is a map of galactic stellar density, and the shaded regions in blue show the results of the initially proposed high cadence regions. So you can see that the structure of the original diamond, which was roughly here, has now, it's slightly fragmented, but it is much more centered on the locales of these high stellar density than it was previously, and it covers more regions and more lines of sight across through the Milky Way galaxy for the purposes of comparing the different stellar populations. Mm-hmm. In order to support other science cases as well as microlensing, you'll see that some of the regions are kind of irregular in shape. And there's a few over here, for example, which are not specific to microlensing. Those are regions of stellar clusters. They are regions of star-forming regions and other areas of scientific interest to other TVS members. And that's the region that those are there. These, of course, are the Magellanic Clouds. They're of high interest already. Those are already included in the revised footprint for the Wide First Deep survey. So Lynn has asked me to include them in this particular map. And I have done so, but with the caveat that this then gets folded into the existing map for the Wide Fast Deep field. So that's where we stood at the time when I submitted the paper. I spent quite a long time analyzing all of the survey strategy simulations that had been done to date, with a view to how well they overlapped this field and what the optimum cadence could be. There are several metrics that the microlensing team have put together. What we have not yet done is look into optimizing basically the refining of the field. We've got to this stage, and this probably takes more time than they can allocate to us. So the next stage is to look at the phase 2 recommendations, which just came out at the end of last year, and analyze that relative to this map, look at more implementations of rolling cadence in the galactic plane, especially for microlensing on different timescales, because that is going to be an issue. It's something that they have looked at in quite detail for the wide, fast, deep, but very few of the simulations to date actually explored rolling cadence in the galactic plane. And that's going to be important for quite a bit of time domain science, not just microlensing, but other time domain science in these areas. And I think at this point, Natasha and Marcus should talk about their work on the specific microlensing metric.
Great, thank you so much. Does anybody have any questions, or you can put it in chat, or you can ask it?
Oh, yes, I am.
Yes, please.
Oh, should I ask a question?
Yes, please go ahead if you have.
Okay. I thank you very much for doing this work. You know, this really clarifies things tremendously over where we were just a year ago. I guess while you were speaking, what occurred to, you know, one of my concerns is this, you know, we're selecting these areas based on what we already know to be interesting. And so therefore what we expect to be interesting when the survey starts. But, you know, we all know that things can turn out differently. And in some sense, we even hope that they turn out differently, and we'll find interesting things that we're not aware of. So I've been concerned about, well, how do we take something like the map that you've made, and as we're doing the survey, how do we know how good it is, or whether we want to modify it sometime over this 10-year period? And one thing that occurred to me, which I'd be very willing to help with, is to also do the mapping of some of the related stellar populations, for example, such as novae, which tell us about where the white dwarfs are. You know, I mean, as microlensers, we want to be able to find compact objects, right? And so where are the novae? Where are the smaller number of X-ray binaries containing black holes in the galaxy, and so forth? And it only occurred to me when I saw your map that it would be very interesting to overlay these on top of your map and to see, you know, what kind of structure that makes, because those might be guides to where some interesting things are. And so if when we start, we're not finding those kinds of interesting things, it may give us an idea of how to move. Or we may even find that they exactly follow the map that you've already made.
So that's a great point. And in fact, that was one of the strongest arguments for using a block diamond, is so that you cover a large area contiguously so that it's efficiently scheduled, but also so that you cover areas that you don't pre-select where you're looking at. And I completely agree with that. And the SCOC has taken the initial map that I proposed, which was advisory rather than this is absolutely what we should do. Mm-hmm. And they are expanding it basically to be a contiguous large survey region, so that it is less of a pointed region, and we have more chance of finding more unexpected phenomena, and also mapping a larger area of the population.
Would they find it useful if I were able to put together just a set of the coordinates of some of these active binaries? Would they find that useful at this point?
It certainly something we can factor in. I would expect those populations to include, to follow the distributions of the stars, which is already in there. And I have included galactic X-ray binary distribution map. So to some degree, I have included those populations in the construction of this map already. That's not to say that it's a comprehensive survey of all galactic science, because there's no way I could do that, but it definitely included a substantial range of stellar populations.
Great.
But as I say, this was just one element of the work on survey strategy that was relevant to TVS. And I know Marcus and Natasha are online. They look specifically at how microlensing observations were impacted by the different survey strategies. And it would be great to hear them speak about their work in detail.
Great. Thank you so much. Is there any other questions? All right. Thank you so much, Rach. It was a really great presentation. And we can go ahead, Marcus and Natasha, please go ahead. You can share screen.
Yeah. Can you see my full slideshow? All
Yes, we
right.
can.
So hi everyone. I'm Natasha Abrams, and Marcus and I will be talking about detecting and characterizing microlensing events with Rubin. So as we all know, Rubin's been going through a cadence selection, and it's important to evaluate the different cadences. We've written the microlensing metric, which is in this Rubinson package, and our goal is to compare these observing strategies, not to actually find the observable number of events. Here we have the phase 2 recommendations from the Survey Cadence Optimization Committee, where the more yellow it is, the more observations are concentrated in that area. As you can see there, this is the kind of smoothed out recommendation map that Rach was just discussing. A lot of aspects of the cadence have already been determined, but as Rach was mentioning, we're mostly thinking about optimizing the galactic plane and LMC and SMC footprint. So the microlensing metric has multiple different metrics nested in it. So there's the discovery type metric, where we've been saying we need at least 3 points on the rising portion of the light curve, with at least a 3 sigma difference between the highest and lowest points. We can also specify a trigger criteria where that has to be satisfied n days before the peak, which would be useful for determining follow-up or the necessity for follow-up. There's also 2 different characterization metrics. So the Fisher metric, which using the Fisher information matrix quantifies how well we can parameterize the event parameters. So for example, the fractional Einstein crossing time error. And the Fisher information matrix is the inverse of the covariance matrix. And also the less computationally expensive, but more rudimentary endpoints metric, which is the number of points within 2t of t0. So the simulated population we injected has a uniform u0 between 0 and 1, a uniform t0 between the start and the end of the survey. The source mags are the mean magnitudes from the tree-leg-all map, which you can see here are actually near the limiting magnitude for Rubin. So we'd likely detect other events more brighter. We inject a uniform TE, but look at small ranges of TE, or the Einstein crossing time between like 5 and 10 days, 10 and 20, etc. We use a 50% blend in high stellar density areas, specifically for the Fisher metric characterization. And the events are distributed according to n squared, where n is the number of stars in the tree-leg-all map. So for those of you who haven't seen this kind of plot before, This is the metric on the y-axis, the different operation simulation or cadence on the x-axis. These are all compared to the baseline V 2.0 survey, and the redder it is, the worse it is, and compared to that, and the bluer it is, the better. So these ones that are very red, you can see are the retro footprint. So this is the 2018 cadence where the original set of white papers were based on, and there's been a significant improvement since that time, since initially very little of the galactic plane was included at all. And then we can look at there's the V 2.0, 2.2, and 3.0. So interestingly, so up here is the Fisher metrics, the set of Fisher metrics with the TE listed here. Sorry for the extremely long names. And here's the number of points metric, and this is the discovery metric. So interestingly, we see more events discovered with this most recent baseline, where we refine the diamond to a shape that's includes more of the galactic plane, but we see less characterized. We're still looking into this, but it's potentially because we've distributed more of our events across the plane. So there are more than 3, but less than the number of points needed to characterize a microlensing event, but we're still looking into this. So just for reference, here are a few of the different baseline footprints. So this was the retro 2018 footprint that didn't include much of the galaxy at all. The more recent V 2.2 baseline, which as we've mentioned, included this rudimentary diamond. And here we have the 3.0, which includes this kind of more interesting shape. So footprint is basically the most significant impact on detection and characterization. So here is for a variety of different survey strategies, the percentage of the galactic plane with at least 600 observations is a function of the discovery rate. So that's the fraction of microlensing events that we injected that we discover for the large range, 30 to 100 days. And you can see there's a strong correlation between how much of the galactic plane we cover versus the discovery rate. And a potential other plot that would be interesting to make would be specifically the bulge versus the rest of the galactic plane, since most of the events are concentrated there. As Rach was mentioning, there is this aspect of rolling. So first, I'll pull up this animation of rolling for those of you who aren't familiar. So on the left, you'll see a addition of all of the observations over time. And on the right, you'll see the observations within like some given time. So you'll see them roll on by. So the first year, the baseline doesn't roll. And then you'll see these strips, which is what they divide the sky into. They just divided the sky into 4 different strips and switch back and forth between sets of 2 of these strips. And you can see them adding up here. Though in the baseline, there's no rolling at all in the galactic plane. And so again, this is compared to the V 2.0 baseline. So these 3 here and the one all the way on the right have rolling in the galactic plane, or in the galactic bulge, since this was specifically for the bulge diamond. And as you can see, there's some potential improvements for very short duration microlensing events on the order of 1 to 5 days. But most of the others are minorly negatively impacted. And especially this is splitting the bulge into 6 different sections, which was definitely far too much. What's it called? It's interesting that also survey strategies that nominally don't rule the bulge actually do have an impact on galactic plane science, likely due to the scheduler. If it's not near the bulge, perhaps it wouldn't go as at the same regular cadence. That would be the case for, in this case, this is the no rolling version at all. Though an important thing to think about with Rubin is do we want more events or more important events? Rubin's in the unique position to look across the galactic plane and to probe galactic structure and how microlensing and other science looks across the plane. Of course, we can maximize our number of events by looking at the galactic bulge, but we should weigh that with if we want to detect at least some threshold of events across the plane, and we can use the microlensing metric to estimate the fraction of events in each coordinate. I'll pass it off to Marcus.
Yeah, so thanks very much. And now comes the part that deals with the characterization of these events. So this was not part of the actual simulation that was going on. So as you know, long timescale events and timescale and lens distance are related to the lens mass, and routinely we constrain TE. For longer, closer events, pi can also be obtained as a fit parameter, but if it's 2 or 3 sigma, if pi e or the magnitude of pi e is actually within compatible with 0, since it's in the denominator of the lens mass. As you can see here, the lens mass is unconstrained. So, and parallax is not part of the microlensing metric, but we are assessing it after the run and also preparing and hoping to have it in a comprehensive system in the future. And on the next slide, you could see if you are taking a simulation, and I will talk about the simulation, where the simulation is from in a second, and plot all the traditional microlensing planets. This is the green field of view that you see, and with the expected location of typical events that we should see in red, you'll see that we are probing a very different population. And we are expecting discoveries in the galactic plane, and also at a different distance level. Also, we will need to rethink what the typical parallax is that can be detected. And on the next slide, we will see what the simulation that we're using is based on here. And that was from 2019, Siddiq Sajjadian and Radek Polaski estimated based on the baseline 2018, as Natasha said, one of the very first ones, the microlensing rate, and they said for the 4-day cadence, they expect 7,900 events or so. And you can see the Einstein time differs depending on the fields that you observe. And we can roughly scale it with the metric that we've seen and give it a boost of 2 or 3, but this is not the real thing and will need to be reassessed. But what it tells us here, overplotting it with the Gaia events, it's in the right ballpark, and this is the one that we could also focus on in the future. And it also tells us something, and it's also the basis for the parallax that we've seen before and where we would expect events. So what is the impact on the observing strategy? And this question we can see on the next one. So where we are looking at 2 test fields here in our case. So we are now getting away from the old simulation because OpSims were updated all the time. And we've selected 2 test cases, test fields, the traditional bulge field and one close to the pencil beam fields Rachel has mentioned in her first talk. So one is the higher cadence field, the other one is the one that we would get. And on the next slide, we would see how that impacts the actual observing strategy. Here we see in a barcode way the sampling in all the bands, color-coded in the traditional LSST coding. The traditional bulge fields are, well, smoothly for the baseline. And for the rolling, you've seen the simulation iterating and rolling through it quite literally. You see the gaps and the re-intensified regions, and with the lower coverage that of the pencil beam. And all of these 4 can now be assessed in a way that we can say something about the characterizing the events, so TE and pi e first and foremost for PSPL events on the next slide. And in order to assess the information, like with the Fisher metrics, we need to figure out what the information content is per point, and it changes with the uncertainty, of course, and also when we observe something, because the sensitivity rules that. And so we use the Rubin sim package in order to use the magnitude error calculation M5 function, and also made that offline available of the nominal uncertainty for the simulation, because on the next slide you can see how a simulation looks. And this was done using the PyLima code from Etienne Bachelet et al., where you can see what the baseline is, and in the background you see the added scatter, what it was actually used to fit it, because we see that the Fisher matrix is also evaluated as part of any fitting package as nominal uncertainty, but it also fitting packages reveal if something is off or the fit is rescaled, and so we are using that here for that purpose. In the next slide, you see how our results look like. This is an efficiency map, and this is something we would like to highlight and suggest for a preparation run for a Monte Carlo simulation, that you're having prepared grids of parameters at hand. And you see the log TE on X and the magnitude of pi E on Y. And this is basically acceptable divided by non-acceptable events in terms of pi E being non-consistent with 0. And so for the difference for two fields, for the baseline, both for baseline, one for the traditional field, one for the pencil beam. The pencil beam here would drop because of its lower cadence, for instance. We say pencil beam, but the pencil beam, it was only chosen close to and evaluated in a way that it is not reflecting a higher cadence would really benefit it, is here the statement. We are overlapping here Casey Lamb's popsicle simulation. And you can see that actually the dark blue one means not characterized. And we think most of this is the case because of using the limiting magnitude as the assumed peak of the distribution and not simulating fully yet the different colors. And if we now turn from the two fields to on the next slide to the two strategies, for instance, the rolling and the baseline, you see there is a actual change a little bit to boosting the nearby lenses, and in particular again on the here we are comparing both the traditional bulge fields. This is why it's not dropping. So there is a redistribution going on depending on your choice of the sampling. So sometimes this can be more beneficial, but in order to compare like with like, we would also have advocate to actually use the simulations and plug them in to that secondary assessment, because these are parallel tasks. This is merging things together that we, on a long-term scale, would like to discuss how to actually optimize that combination in the future. So, and with that, we'd like to conclude on our last slide. And no, not yet. I was one ahead. So also you can use that in order to simulate planetary light curves. And it is very much OPSIM dependent. Long events like this one seem to be characterizable. If we see such a feature and think it's 170 days, a stellar event will certainly be shorter. And we had to boost the limiting magnitude, the magnitude of the event by 4. In that case, it was accepted in the simulation as characterizable. So for planetary events, we would think that follow-up will also play in the future a major role. Unless the strategy is changed or some particular simulation suggests something else. So, but now we should conclude.
Yeah, so to summarize, in the most recent survey strategy recommendations, is a 3 times improvement over the 2018 baseline strategy, and the more recent optimizations have had impacts on the 10% level. About footprint has the largest effect on how well we do, so we should carefully think about how best to optimize it.
Yeah, and the characterization of long duration events with Rubin data alone is possible, but ideally the brighter ones will play a major role and need to be factored in here. And we would need some further input on the expected DIA blend, which is of course not trivial to obtain. Short duration and planetary events will certainly need follow-up in order to get them fully characterized. But for the exact numbers, we would advocate and we would suggest to talk about the setup of the Monte Carlo and comprehensive simulation. Thank you so much.
Thank you so much. It was really great. Is there any questions? Yanis, yeah.
Yeah, I just wanted to ask if Natasha and Marcus are planning to run a simulation that includes follow-up facilities for characterization of short time scale events.
Not, I think this is more addressing the part I was talking about, not within the scope of Rubin. I think the Monte Carlo simulation can then be used to assess the impact. Whenever you have a Fisher matrix, you can add more data points yourself. If that is publicly available, then you can, for a given setup, calculate your contribution, which is the clever way that information is additive.
Roseanne, please go ahead.
Okay, well, you may already have covered this, but especially in terms of parallax, I'm wondering, are we planning, as we begin to see things rise from baseline, to do a cross correlation with Gaia or other catalogs? Because if you know that you have a nearby object, I think that's kind of interesting already. And then my other technical question is, when we are doing the parallax fits, how does that compare? How far out are we successful compared to how far out Gaia is able to make good parallax estimates?
So the traditional approach of it was that Gaia and Rubin are supposed to be complementary, as that was published originally. So they limited the magnitudes. The bright events will be seen from Gaia, that Gaia will alert as part of the Gaia science alerts, as long as they are operational, will indicate and give us a clear picture of the bright end. And this will be automatically covered. Also, mind the lifetime of Gaia will come to an end in 2 years' time, in 2025 or so. And so this will not be a perfect overlap, and there will be some predictive power for the brightest ones, but most of the events will be disjoint, I suppose. But there's the lovely plots by eVisage at a long time ago, the showing the complementarity of the two missions, and that gives you an idea.
Well, I guess what I was thinking is, as the data is coming in, right? What procedure do we follow? I mean, even in principle, we might already see something that's high when an observation starts, but we know it's associated with a Gaia object for which we have a measured parallax. So it's simply the fact that we have the measurement. It's great during the time Gaia is up. What a fantastic thing. But when Gaia, even when it's not there, we can think about cross correlation. And, I think, unfortunately, most of the time when we see some kind of signal from a Gaia star, it will likely be intrinsic to the Gaia star, but a certain fraction of the time it will be lensing. And so I'm just wondering, are we planning to implement procedures that take advantage of that?
There should be a whole team preparing for that, actually, a group working on the cross match with these catalogs. I'm not sure if they say Gaia, but if it's only the catalog, that's for sure the case. The science alerts, I'm not sure about. I'm not sure if they were aware about that part, which probably would be a good thing to check.
Great.
Thank you. Ray, question.
Sorry, I had to find the right button to unmute. Marcus is absolutely right that there are groups, actually multiple groups, working on the cross-matching of the LSST catalog with other surveys. And definitely Gaia is the low-hanging fruit. And yes, it does have a certain predictive power, and I agree that we should cross-match with the alerts, but I wonder if Gaia's real value in microlensing is going to be characterizing source stars up to a point, so that we know at least the characterization of well, we should get a rough spectral type from the two Gaia colors, and we will get its astrometric properties, but it will not go very deep in the bulge. That's its main limitation. I think in the rest of the sky, it's probably more useful.
Thank you. Roseanne, we have like 1 minute. We've got.
Just briefly then, I've been very interested also in lensing by nearby stars of things in other galaxies. And so these would be something that would be primarily out of the plane. And that's a particular area where we might end up with a kind of a very short event, but one which would be of particular interest. So that's all I wanted to say.
Yeah, sounds great. Please, I mean, you can add that to the list of the project ideas. It'd be very interesting to discuss. Thank you. Thank you so much, Natasha and Marcus. A very great talk. And our next talk is the project that has been undertaken by Annabelle, and it's on the Rubin-Roman synergy. Annabelle, are you?
Yes, can you hear me?
Yes. Yes, please go ahead and share a screen.
Yes, 1 second. Okay. I can't turn on my camera, I'm sorry.
No worries.
Okay. Okay. So, well, my name is Aníbal. Today I'm going to talk about this work in progress that is happening in the Microlensing subgroup. The title of this work is The Impact of Rubin Precursor Observations on Microlensing Events in Roman. And so what is the idea about this work? So Rubin started his science operations in 2024, and Roman mission will be launched in 3 years after, in 2027. And one of the main Roman surveys is an exoplanet search in the galactic bulge that will be carried out with a high cadence in a 2.2 square degrees regions that will be also seen by Rubin. So let me be a little more specific about this, the objective. We know that a flat baseline is the key to distinguish a microlensing event from other type of variability. So since Rubin will see the same sources before Roman start his science operations, we can measure the baseline of those sources. So in this work, we want to answer if these observations will improve the microlensing event detections made by Roman. So we have two ways to answer this. In the two, we must simulate light curves for the two telescopes, Roman and Rubin. And one way is make light curve fits of planetary events, and on the other hand, we think make a study with of the identification of microlensing event using machine learning. So how do the light curve simulations? In this flowchart, I explained that if we first start with a source simulation with Trilegal. Then we, with the Roman noise model and cadence from Matthew Penny, and the operation, and on the other hand, for Rubin, and with the operation simulator, and the noise model from IB6, in the same way that Marcus said in the in his talk, adding the Gaia spacecraft positions, because Roman goes to L2, the Lagrange point. So we use these ephemerides, and we combine all this in one pi-lima simulation for binary lens in this case. And here we see the trilegal magnitude distributions for a point in the pulse. And here are the noise model for Roman and Rubin. And okay, let's see an example of a light curve. Here in the right, we can see a light curve of a binary event, and the parameters are sampled from these distributions. For the Einstein time is a log normal distribution. Then for these parameters, we have uniform distributions, and for the parallax parameters are normal distributions. So in the first way to answer if the Rubin observations improve the Roman detections, we want to make fits of these light curves. So let's see an example of a fit with only the Roman data, and another fit with Roman and Rubin data. And if we see a comparison of the for this particular example, there is for this particular example, there is no an improvement by using Rubin in addition to the Roman data. These are the parameters, and these points that seems the same are the fit of the Roman data and the Roman plus Rubin data. But this is a very preliminary result of this one light curve. Like I said, this is a work in progress, and we must investigate this for a well distribution of the event parameters. And okay, something that is a caveat is that this fit took about 14 minutes on the link framework with these options. So we must improve this on the simulation. Okay, so and the other way of this project was identify events with machine learning. So this simulation of the light curve is the same, but now we want to classify the microlensing light curve that we simulate, and also we must simulate other types of variability. So we use the software Microlia that was made by Daniel Godínez, that has these three algorithms: the random forest, neural networks, extreme gradient boost. And our objective is use this classifier to assess the improvements of adding Rubin data to identify microlensing events in Roman. So we show some preliminary results using the Elastic dataset for training and validating with this Microlia software. The dataset of Elastic and plastic are these categories for the galactic classes. We, for the result that I will show, use these classes only, and we balance the dataset that we use. The elastic and plastic dataset are very unbalanced, but we balance it first. So this is a result of a classification in all bands of the Rubin data. This is how Microlia works with Rubin data. This is the precision, recall, and accuracy that we can see that are pretty good. And but the way that we make this classification is using like a mean of the probabilities that the classifier makes on each band. So it's not so good, and is something that we must improve. Okay, this is the confusion matrix normalized and normalized. This is the number of light curves. It's the same in all the classes. Okay, that's it. This is our this work in progress. We have work to do in the side of the light curve fitting. We must parallelize the runs for a large number of configurations and make a statistical comparison of the results with and without the Rubin data. And on the other side, with the microlensing classification with Microlia, we must optimize the use of all bands for the classifications, adding the Roman data. And we also must do some benchmark with other light curve classification methods, including those running in Elastic. And also, we must make a statistical comparison of the result with and without Rubin data. That is the main idea of this work. Nothing more. Thank you.
Thank you so much. Such a great work. Is there any questions for Annabelle? Rosen, I see your hand is raised. I don't know if it was for the previous question that you asked or if it's a new one. Okay. All right. Etienne? Yeah, please go ahead.
Hello, you hear me?
Yes.
Yes. Thank you. And sorry for the late registration.
No
Sorry
worries.
about that. Yeah, good talk, Annabelle.
Thank you.
Regarding the confusion matrix you get on the classification, I was wondering if you can, or if you have the statistics of failure for Microlens, depending on, I don't know, something like U-naught or maybe the blending ratio. Do you know that? Like in the sense,
no.
like you fail to detect event with a very low signal, maybe, or something.
No. However, I don't understand quite well the question. Can you explain me?
I see in this matrix, for example, you have 27 microlensing event detected as EB star. So I was wondering if these events are particularly low signal, like a very small peak, almost no signal in, right? So it's hard to detect.
Yes, I don't have those results here. I can search, but no, I don't know
Okay.
right now.
Okay. Okay. Thank you.
If I may interrupt regarding this question.
Yeah.
Yeah,
Yes,
sorry.
yes, please.
just to say, I mean, I never looked at that. There are no plots in this presentation, but he looked at the systems that were missed, and some of those were, like you say, you know, very low signal to noise. Even by eye, you could not see like a microlensing shape. So this has not been quantified. I mean, which fraction of the ones you missed you may be able to find, and those that really there is no information that you could ever use to find that. We did not split into these two categories, but clearly there are many, like you say, that they have just low signal to noise, or even that you miss the peak when there is the timestamps. Yeah.
Yeah. So one way that can be easy to do is to plot histogram of U0 for the different category, like the good classified versus the bad classified, and you compare the distribution, and then you will maybe realize that, okay, they are almost, you know, impossible to detect or something like this. I don't know.
Right. Yeah.
Thank you.
That's a good idea.
Yeah. Thanks. Rachel?
Thanks. So Annabelle, one thing that occurred to me as you were speaking is would be great to compare the detection algorithms in Microlea with some other implementations, just as a comparison to see how well the tools do. And I believe that the Antares broker does include a microlensing detection algorithm, but I don't know if it's yet on a public alert stream. So
Okay.
I wonder if one of the things that we should all do as part of this workshop is to consider engaging with the alert brokers for Rubin to make sure that there's more than one algorithm out there trying to detect microlensing in Rubin alerts. Because currently Microlea is used by the Fink broker, which is great, but that's just one broker. And it would be great if there were multiple implementations.
Right.
Right.
Martin?
Yes, thanks. It's a comment on Rachel's comment. Yeah, so yeah, we agree it's very important. Actually, there is a group from Brazil, which is from my regional institution, that they are working with the Fink broker to classify events in general. So they have they have developed a long short-term memory algorithm, and they are looking at all classes of events. So we have this classifier, and we want to compare it with Microlea, like you say. Yeah.
That's great to hear. Thanks.
So this is on the Elastic dataset, which is the same dataset that Nibble ran Microlea. So
Great. Thank you so much. Is there any other questions for Annabelle? Okay. If not, we can. We were thanking Annabelle again for such a great work. And our next speaker is Yanni.
Yeah, I'm here. Thanks,
Yes.
Maya.
Yes, and he's going to talk about the new updates on the Pylima package. And I just want to mention, since it's not written in the agenda, but after this talk, we'll have a 10-minute break, and then we will start the next round of talks. Thank you.
Sounds
Yes,
good.
please
Thank
go
you.
ahead.
All right, let me just share my screen first. Can you see this?
yes.
Okay, great. Okay, so Pylima is a microlensing modeling software that's been developed. It's actually the first microlensing modeling software that is open source, completely available for anybody to use. The link is down there on GitHub. It was developed by Etienne, who is here with us. And it was originally released quite some time ago, 2017. So the way that it was originally implemented, you could load the data and assign a model to it, and the fitting functions, they were all kind of strongly codependent within the original code, all of these three elements in the fitting. And there have been many, many years of user feedback and useful suggestions for improvements. So over the last few years, Etienne has been working on developing the second version of PyLima. And the new version is currently in a beta testing, I guess, phase, we would call it. So it expands on the functionality and reinterprets some features to address multiple user requests over the last few years. Okay, so how does it change things? Okay, so the new version includes expanded fitting algorithms. So you can choose differential evolution, MCMC, combination between DEMC, and many different others fitting algorithms. You can also define your own if you want. So the data, the model, and the fitting functions are now handled as separate objects within the code, so it's much more easier to manage. In terms of new features, it includes astrometric microlensing, and that's the relevant paper over here. And it also includes full Keplerian orbital motion. And there are new features that are still being developed. These two are more or less available right now, and the new features are still being developed and tested. So it's much easier to use, and it adds new methods and features compared to the old one. The only problem is it's not backwards compatible. So the old version is not supported anymore, and going forward, it's only this new version that is going to be supported. You can actually find it if you go to the PyLima GitHub repository. You can download the new version under the branch called Rebranded. So you can install it and test it out. So let me just share the next part now. Okay. Okay, so what I want to do is we've been working with Etienne on a number of examples for the new version. And I think we have enough time to go over the first tutorial. Okay, so this tutorial shows how you can fit a simulated data set. So it simulates some data and does very simple fitting. Okay, so first you have to define, import all the libraries that you need. And then you import an event, and you import. So this is the object that's going to hold the event that you want to fit, and the telescopes that have observed this event. This also includes if you have one telescope with multiple filters, you have to define a separate telescope object for each different filter that you have used. Okay, so you can create an event and you can give it a name. Okay, and then you can load up the data, and this is the structure to load in the data. You just take a standard format data set. So this is, you have the HAD, the magnitude measurements, and the errors in the magnitude measurements, but you can define your own if you want, as long as you tell PyLima what the format is. Okay, and then you have, here I'm defining two telescopes, essentially two data sets. One is the survey data, which we're simulating Ogle, and like a follow-up telescope, one of the LCO telescopes in I-band observations, okay? So the data are already pre-formatted in 3 columns. So you have the time, the magnitude, and the error in the magnitude, and that's about it. Okay, so once you've defined these data sets, then you have to associate the data sets with the event that they correspond to. Okay, so you append this data set to this event, and then you have to say, okay, so when you want to plot them later, you have to define which data set will serve as your baseline, as the data set upon which every other data set is shifted to match. Okay, this works for all ground-based data sets. Of course, if you have space data, this is plotted separately, and there is an example later that shows how to do that. Okay, so once you've done that, you've associated the two data sets with your event. You've defined, the survey telescope that you want to use, and then you can run some checks to see if everything is working fine. And then you need to construct a model, okay, that you want to fit to your data, and then you need to link this to the event that you have prepared. So let's try a basic point source pointless model without second order effects. So the function that contains all the models in PyLima is called .model. So from PyLima.models, you import the PSPL model, okay, and you associate that to your event. And then once you have defined the model, then you can just fit it, okay? And you have to choose a fitting algorithm. For this example, we use the LM algorithm, but if you want to see the PyLima documentations, there are multiple different algorithms available to use. Okay, so you define the fitting algorithm, and then you basically tell it to fit the event. Okay, you can declare a simple fit object using the model you defined. And then you can, if you want to see what parameters, what the initial parameters here, this is the parameters that we're trying to fit. So it's T0, U0, T, and the source and blend fluxes for each observatory. Okay, so the more telescopes you have, the more parameters like those you're going to have to fit. And this you don't need to define. This is done by PyLima automatically, but you should be aware that they are there and they are being fitted. Okay, so once you've done that, then you can just fit the event. Okay, so you have the initial parameters. You can also give it some guess parameters if you like, and it starts from those, and it returns the fitting parameters and the chi-square of the fit. Okay, so then to view your results, you can just type myfit.fit results, and it gives you all the parameters plus the covariant matrix. Okay, so it keeps, if you've run, for example, an MCMC chain, you can actually look at the entire chain. You can print out the chain and the information, and it keeps the best model that it's got in a little parameter called best model. So this will give you the best fit results. Now, if you don't remember which parameters its entry represents, you can always access the descriptions from fit parameters.keys, and it will tell you what all of these are here. Okay, so we've done the fit, so let's look at some plots. PyLima offers you some plotting tools that you can use. Of course, you can use matplotlib to plot it yourself. But if you're a bit lazy, then you can just use the PyLima plots. So to plot light curves, you just call from PyLima plots.plot light curves. You tell it the model that you're using, and then you give it the results of your fit. And so you can either input the parameters themselves. So if you just copy paste the parameters here, okay, it'll still work. Okay, and then you can just view the results. Okay, so this is our PSPL fit. Okay, you can zoom in around the peak and see if it's good. So clearly there is something that is not fitted perfectly there. You can see in the residuals that the peak is not fitted very well, and this tells us there are some other effects in there. Okay, so let's try the algorithm differential evolution. Let's try this fit. Okay, this takes a bit longer to run because it explores the parameter space. Depending on the complexity of the model that you're trying to fit, this can take a very long time. Because this is a very simple model, this should converge relatively fast for us. So we can actually look at the results. So it's already converged. And you've got the best model over here and the likelihood of the best model. Okay, so now we do the same thing. We just plot the results of our second model after the DE run. And you can see here, if you zoom in again around the peak, you can see it's done a little bit better. Okay, but there's still some residuals left. Okay, so if you zoom in, this event shows strong finite source effects. Okay, so let's try to include that. So what we're going to do now is going to import a finite source point length model. Okay, and then try to fit that. And we do another DE fit. Now we're adding the finite source effect. So we're adding another parameter in there. So this is going to take a little while. And then once it's done, then we can look at the plots and zoom in and see how well it's done fitting the peak. So you can see it's still running there. So usually with binary events, if you're fitting a binary model, this can take quite a while. There is the option to switch a progress bar so that you see how far it's gotten. When you're running it like in production, when you're fitting a complex event, you can actually track how far it's gone. Okay, so then we can look at the event again, zoom in around the peak and see if the finite source has done any better. And you can see it's done quite a bit better. Okay, but here, over there, you can see there's still kind of some structure, okay, around the edges. And this is indicative of limb darkening. So what you can do then is you can say, okay, well, I have the limb darkening coefficients for this event, so you can define the limb darkening coefficients for each of your bands, and then fit again. Okay, and if you do that, this is basically the approach that you would follow for fitting any event. Okay, you keep adding extra parameters and see if there is still residuals, and then you introduce additional effects. Now, this particular event is relatively simple because it's a finite source point length event with some limb darkening. Okay, so it doesn't take very long to fit. Okay, and once you've got that, okay, then you can zoom around the peak again, and you can see now at the residuals, it looks like the structure is gone. So it's a lot better. Okay, now if you want to run an MCMC run, you can do that as well to explore, how the parameters kind of the correlations between the parameters. Okay, you can define an MCMC run here. Okay, so you import an MCMC fit and then you run a finite source point length and you use the previous parameters from the previous fit as seeds. Okay, so this is what I did here. Model parameters guess is equal to guess parameters, which is the results from my previous fit. Okay, and then you can run an MCMC run, and then we can look at the correlations between the fit parameters. So it's very, very simple. All you need to do is you need to define an event, associate some data with it, and then ask for a model to be fit, and then just fit the model. And then you can look at all the distributions. The only thing that's a bit troublesome is the more complex the event that you're trying to fit, and the more data, obviously, that you have, the longer it can take until it converges into something reasonable. And with MCMC, this is the MC package. So you have the progress bar, and you can see it's almost done. And then we can, once we've got that, we can actually plot the chains for the. So you can see how the chains, kind of the MCMC chains, have progressed. So you can explore that if you want. And then you can see the MCMC results, the model. This is the actual model. This is the fit. And these are the errors. Okay, so you can plot now, once your MCMC run is done, you can plot the correlations between any two parameters. Okay, so we can just plot them as a 2D histogram. So let's try to plot U0 against TE, for example, and we pick the last 1,000 at the end of the chain, 1,000 chains. Okay, to look at where it's sort of has started to converge. Okay, and you can see the distribution of U0 compared to TE, how they're correlated. Now, of course, you can produce that for any parameter that you want. Okay, so that I think that's my time basically. Now there are 5 other examples that show many different things that you can do with PyLimit. You can use it to simulate an observing run, as Marcus showed before. You can use it you can define your own parameters. If you're not happy with the standard Microlensing parameters, you can define log TE or whatever that you want to fit. You can define your own space telescopes, artificial space telescopes, or use existing space telescopes to see like what your event might look like if it's observed at a certain cadence that you can define from space and so on. And the last example that we've done with Etienne is the procedure you would follow to fit a real microlensing event. So all of these are available for you to test out and download. And if you have any questions, you can just ask us on GitHub or email us. So I think I'll stop here and take any questions that you have.
Thank you so much. It was very useful. Rachel, please go ahead.
Thanks. So yeah, a couple of questions. The first is, I understand Pylema 2 has support for astrometric microlensing now, and I was wondering if you were thinking of adding a notebook example to GitHub to show users how to work through that workflow.
That is certainly something that we want to do, okay, but we're working with example by example. Yes, we would like to include examples like that. We would also like users to actually submit their own examples. If they've worked through a particular thing that we have not included as an example, they can email us and we would be happy to include extra examples. So what we want to build gradually is a library of examples that users can find useful.
Cool, I agree. That would be really helpful. The other question I had actually relates to astrometric parameters, in that Annabelle was working recently with using Pylema to model the predicted microlensing parallax from the Roman spacecraft. So for that reason, he was using input from JPL Horizons on exactly what the trajectory of the spacecraft would be in order to work out the parallax signature. And we discovered that JPL Horizons has recently updated its formatting of its tables, which led to some confusion. Now, is that something that is now resolved in the new version of Pylema?
This is something I think that Etienne is best equipped to answer, as I have not had any problems with ephemerides. So I've tried simulating Gaia and so on, and other telescopes and Spitzer. I don't know whether I have not had any problems personally, but I don't know if Etienne has experienced any. Maybe he can.
Well, I hope it works. But yeah, for a separate project, I also realized that GPL has changed some stuff. But in the new version of Pylema, what we do for the GPL query is to use AstroPy actually, rather than the very nice team lister function, which was very good, but a bit outdated, let's say.
Yes.
So
AstroPy is better supported.
Yeah, I will think so.
Oh, good.
So if AstroPy do their job well, great, that should be the case for Pylema too. Then, but you still thank Team Lister for his nice routine for the first 5 years. That was very nice.
Yeah, for sure. No, I think it's wise to go for AstroPy, since that is now officially supported. That's a good choice. Thank you.
Thanks. We don't have time for one more question. I think if that's okay, the other questions can be on the Slack. Roseanne, you please go ahead. But
no, my question might be a little bit complex. So Natasha, why don't you go ahead? You had a question as well.
Okay, Natasha, please go ahead.
All right, sure. It's actually a very small question. Just for reference, how long is quote a while for these more complex events? Like, yeah, about how long?
Okay, so I'm fitting one of the Gaia targets right now, and we have a very large data set on that one, which I've had to bin in order to speed it up. So this is a model that includes parallax and Keplerian orbital motion that I'm testing, and it can take usually I run long differential evolution searches as to get some starting parameters for my MCMC runs later, and these usually can take about a day or so on my personal computer. So you can run it on your laptop, but it does take, I mean, you know, if you're fitting something very complex, then it can take about, you know, about a day. But it depends on how much, you know, how much data you're fitting and how complicated your model is.
Thanks. And I guess a follow-up question is there support for parallelization in Pylema?
Yes, there is.
Okay.
So if you have multiple cores, that will go much faster.
Thanks.
Thank you. Roseanne, if you can put your question in the chat, and then I can put it on a Slack, or if you want, you can put it on a Slack, and Yannis can answer it there.
Right, or else, you know, I think
Right.
both Yanni and Etienne, I might want to chat with them offline a little bit.
Okay.
As I said, it's a little complex and probably, you know, it needs to actually be discussed a little bit. But thank you. And for both of them, I think this is a fantastic community service. You know, what a
Yeah.
wonderful tool for everybody to have.
Well, it's Etienne's work, so I'm only working mostly on the example, so it's mostly Etienne that's developing this.
Yes. Yes. Thank you so much. So we can have a 10-minute break, and we will resume the talks at 12:34 Eastern time. And after that, Steve is here, and he will talk about the in-kind facilities and telescopes available through in-kind contributions to the microlensing subgroup. Thank you so much. I will see you after the break.
See you
Thanks,
soon.
Samaya. See you later.
All right. So hopefully everyone's back from the break. Our next talk is on the facilities and telescopes as part of the in-kind contributions available to the microlensing subgroup. And we are happy to have Steve here from the in-kind contributions team. Steve, please go ahead.
Hi, thanks for having me today. I'm real excited to tell you about some of the opportunities that will be available through the in-kind program. And let me go ahead. So I'm part of the Rubin Observatory operations here at the NSF's NORLab facility and work as part of the in-kind program team. For those of you who are unfamiliar with the in-kind program at Rubin Observatory, these are international teams making in-kind contributions to the Rubin community in exchange for data rights to the survey. You can see that these span things from what are called like IDACs, which are independent data centers, from data sets, software development, which is the largest part of this that goes both to the Rubin Observatory itself and the science collaborations, efforts to help with commissioning. And the part that I'm going to be talking about today is the telescope time. So these are in-kind contributions where they're giving telescope time to the Rubin community in exchange for data rights. How does this work within the Rubin operations? These contributions are managed first and foremost by program managers within each program. So there are sort of contribution leads that lead each contribution. Each country's program is led by a program manager. And we facilitate this work within the in-kind program coordination team by a group of IPCs that we report directly and work directly with the Rubin director and deputy director of operations here. We have a website within at the Rubin websites that describes the program and also lists all the different in-kind contributions that are coming and answers a lot of questions. So that if you have more questions that go beyond this, that's an excellent resource. So telescope time opportunities, the main reason I'm here, tell you about some of the exciting opportunities that we have through this. I just want to give a couple caveats. The data rights agreements have not been signed yet with these individual programs. We're working with that, lots of lawyers and contracts and things. And so everything is sort of pending until those data rights agreements are fully signed. And then another caveat that everything is sort of really pending until we actually announce something is available through like a call for proposals. And so I'm going to tell you about specifics today, but just know that everything is sort of complete, it's not finalized until it is actually announced. We want to match the time frame of availability of the resources to the survey. This varies by program. So as the survey first light continues to be pushed a little bit into the future, we are trying to work with these programs to make sure that their availability of their resources and their facilities are at the same time. We don't want to have telescope time made available for years before the survey begins. That kind of hurts the availability of doing follow-up with that time. It is probably some of the dates are already starting to be in conflict with that, but we're working with them this year. Everyone's sort of slow, and so they're usually pushed. So there's nothing likely to be announced until sort of like the 24A semester in terms of actual telescope time availability at the earliest. But I'm working with them now to try and set that up and get it as closely matched to the actual survey. I'm only going to talk about the opportunities that are part of the in-kind program, not just the other avenues that are available through NORLab. So there's also, the US time through all the NORLab facilities, Gemini, and the MSOs and things like that. Some of these are overlapped, and the way that this will be available, so I'll talk about it, is through NORLab, but I'm only including the actual in-kind contributions. So there are a number of different size facilities that are going to be available. These are the very largest of the 8 to 10 meter class facilities. So Subaru is giving us 5 nights of time per year, which includes access to PSF, their spectroscopic facility that is coming online very soon, and so we're going to have very good preferential access to that, which is very nice. What isn't included, like in this mention of Subaru, is that they're also giving time as part of their filler surveys for their PSF surveys and some additional PhotoZ data sets and things like that that are being handed over to Ruben. But this is just open access time. So these 5 nights will be available as PI driven access. GTC in the Canary Islands is giving about 5 nights per year. I'm saying about 5. There's 2 programs, one at 2 nights per year and one about 1% of the telescope time through another program. And so that's about 4.7 to 5 nights per year for that facility. And again, these are all open access. SALT in South Africa is about 50 hours per year as well. And we're still working on getting exact timeframes and firming up access to the LBT at Mount Graham in Arizona via the Italian in-kind program. So a modest number, but certainly an increase over what is available now to access to these large facilities. There are far more in the sort of next tier, these sort of 1 to 4 meter classed telescopes that are going to be available through this. So Korea is contributing 300 hours per site per year for their KMT net. So these are 3 different facilities spread out across the world. This will be a combination of TOO time. So they're making like the first 30 and the last 30 minutes of every night available for TOO, rapid 24-hour turnaround observations, but also observations on pre-assigned nights. Taiwan is building a new telescope, a 2-meter telescope in San Pedro Martir in Mexico. And we're going to have access to that at roughly 40 nights per year level. Turkey is making 23 nights per year on their 2 1-meter and 1.5 meter telescopes at their national observatory. Again, South Africa, in addition to their SALT time, is going to give us 52 hours per year now on their facilities, which range from 1 to 1.9 meter. They also sort of have hosting time available through a lot more facilities that may also become available through this, but we're still working on that. We're working on providing at the Mount John Observatory for New Zealand, 20 nights on their 1 meter, which is, and then 20 equivalent nights during the New Zealand summer on the 1.8 meter. So this is the survey telescope that they use for Japan on the MOA survey, for their microlensing survey. They have 3 months in the summer, which they have use for it. Those are very short nights in New Zealand. So we're sort of working on 10-hour. So about 200 hours of time available during that period, during the summer nights on that for access, which fills in a nice longitude data point for complete world access. And we're also working towards access on the 2.6 meter on Paranal VST telescope via the Italian in-kind facility. There are a few other little facilities here and there that we're still working, but these are some of the major high points, I think, on these. There's a lot of other facilities. So in Argentina, we have almost 3,600 hours per year on small facilities in Argentina at various sites that'll be available. We're hoping to be able to make available about 3.6 days per year on Deep Space 3, which is this sort of communication satellite for ESA. And so they have time as hosting facility, and this is a 35-meter radio telescope that'll be available. And then we have over 3 years, we're going to have about 287 hours on the Nordic Transient Explorer, which is available on the Nordic Telescope on La Palma. This is primarily going to be supernova work, so I just threw it in here as the other because it probably will not be as useful to the microlensing community, but these things will be there. How will this telescope time be available? It's going to be offered via the NORLAB time allocation process. So if you're familiar with applying to US facilities through NORLAB, you will be familiar with applying for this time. Just as a reminder, we have a dual anonymous 2-stage review for those telescope proposals. And we expect that this time will be available under the NORLAB Open Skies policy. So this is time that is given to the Rubin community for access to the Rubin telescope, but the time is not being specifically allocated just for Rubin science. And part of that is because, of course, a lot of US funds and things are going into the Rubin telescope. And so this also can benefit those science that does not necessarily depend on Rubin. But we want to make sure that it fulfills the need of the Rubin community as much as possible. One way that we want to look into doing that is to be able to take a portion of this time, perhaps about 20%, which would be comparable to the other amounts of time on other telescopes for these sorts of things via survey or long programs, so that you can apply for a very large program or a very long-term program to be allocated with using this telescope time. And we found that to be helpful for sort of the big science questions that need to be answered that we expect to be explored within Rubin Science. Some of the programs are going to have different allocation paths, especially the large facilities. So like the GTC and things like that may not go through NORLAB, that specific NORLAB time allocation process. But the general idea is that it will. NORLAB has a long history of making telescope time on other facilities through like the TSIP program or other sorts of exchange time. And so this will look a lot like that. Just a brief talk about AON integration. Rachel's going to talk more about TOM toolkits and things, so I don't want to say too much. Just that a large number of these in-kind facilities, especially the sort of 1 meter class facility and up, not necessarily the big facilities, but the sort of next tier, intend to offer some sort of AON integration. And like I say, at some level, it's this varies in their sort of plans to sort of web-based interfaces for submitting the observing details. And retrieving data to far more realized implementation. And that we realize the success of Rubin and LSST follow-up work is going to be the better the integration, the more ability for these to tie in through AON and the brokers and things like that to do follow-up work, the more successful these will be. So we really want to encourage these facilities to have the best integration that we can for our community. And so we recognize that a lot more work has to be done in the space over the next couple of years to try and get these facilities up. A lot of these offerings are going to be for the 10 years that the survey is running, so through the 2030s. And so we want to make sure that we get it right now, so that these are very successful programs over the next decade. There are lots of resources. If you have questions about in-kind programs or about facilities, that'll be available. I just list some of them here. So there's the web page that we have through Rubin. If you search Rubin in kind on Google, it brings you to this page. We have this sort of help desk system, jkh@lsst.org, where you can email us and we make sure that inquiry gets routed to the right person to help you answer this. We are also on the Rubin Slack. So if you have access to the Rubin Slack, we have a channel called Alps in Kind Ask the IPCs. You're welcome to talk to us there. And of course, we maintain a presence on the community forum, which is another good opportunity to talk to us. So that was just a quick overview of a lot of the facilities and the things that are there. I wanted to leave some time if people had questions. I feel that sometimes just the informal chat is often a good way of talking about these opportunities. So I'll stop sharing now.
Thank you so much. It was a very great talk. Is there any questions for Steve? Rachel, please.
Hi, Steve. Thanks for that overview. And it's really great to see the range of resources that we'll be having access to. I have a couple of questions I wanted to clarify. You mentioned that the time will be allocated under the Open Skies policy. Does that mean that people outside the US will be able to apply for this?
If that holds true, yes, then that does imply that they'll be able to do that. Of course, that Open Skies policy has always represented that you have to explain why your the availability of resources does not, leads you to need to be able to use the U.S. facilities. We think that basically, if you're from a facility that's devoting to the in-kind program, no, you won't be able to ask for more time on your own facility through the in-kind program or through these things. But in general, we want to make this. The U.S. has been a strong supporter of the Open Skies policy and continues to do so.
Absolutely. And if I might put my TOM Toolkit hat on for a second, I know we have spoken previously about supporting some of the in-kind proposal telescopes to become compatible with AON. And we've mentioned previously about the idea of doing a workshop for the telescope operators.
Yeah.
So from the TOM side of things, we are keen to take that forward maybe later this year, because it seems like the time is pressing, but I appreciate if the contracts have not been signed for the data rights agreements, there may be some delays from the telescope operator side.
Yeah. I'm in the process of starting to really contact one by one each of these facilities and really sort of start talking to them about what their exact plans are, and mention that we would like to do a workshop, see if they would be available, especially wanting to make sure that their technical staff that is going to be doing this implementation are going to be available, because I think that's going to be key into getting it right, not just having somebody who's looking at overviews. And so yeah, I'm hoping within this year that we can make that happen, and I think that'll be good for everyone, especially these facilities, and getting them on the right path.
Great. Well, let's touch base about that offline.
Yeah.
Thank you.
Thank you so much. Martin, did you want to ask a question? I saw your hand raised, but
Thank you. It was the same question asked by Rachel. Thanks.
awesome. Okay. All right. So, is there any other questions for Steve? All right. Let's thank Steve again. Thank you so much for this presentation. All right, and our next speaker is Rachel again, and she's going to talk about the TOM toolkit for microlensing follow-up. Rachel, please go ahead.
Thank you, Samaya. And let me just share this screen 1 second. Okay, hopefully you should be able to see my screen here.
Yep.
Great, thanks. Okay, well, hello again, everybody, and thank you for the opportunity to tell you a bit more about the TOM toolkit. I'm excited to present some of the tools that we've been working on for microlensing, and also to feature some of the new developments that the team have been working on. But first, allow me to recognize the development team behind this project, in particular LCO software engineers William Lindstrom, Joy Chatelain, and John Nation. So, as we've heard, Rubin will bring an enormous wealth of discoveries, but discovering the survey alerts alone is not the same thing as physical understanding. So the challenge, once we discover these things, is then to synthesize all of the available information in real time and decide and identify the most important targets, and also identify those for which Rubin data alone may not be enough to fully characterize the event. And for that reason, it's often very important to decide in real time whether or not you need to select a target, and if so, what observations to make. The challenge for Rubin, of course, is the massive amount of data. Synthesizing information on targets of interest is going to involve managing a lot of data, and if you add follow-up observations into that as well, then you have to potentially manage a very large program over a very long period of time. And that's where software tools can help. So target and observation managers, or TOM systems, are software tools that are designed to streamline the workflow and reduce the overall human workload. So they make the whole process of synthesizing information and implementing a follow-up program much more efficient. So TOM systems can take advantage of the programmably accessible services that are out there, such as the alert streams, the brokers, the data archives, and they can retrieve the information relevant to a target and display it all in a single place for evaluation. And the advantage of using software tools to do that is that users don't have to reinvent the wheel. Interfaces for those services already exist, as well as a number of interactive data visualization tools. But TOMs are also a platform for communication. The humans involved in a project are often geographically distributed, as we all are. And so having your data accessible through an online platform means that everybody can get access to the data, can post comments, coordinate follow-up efforts and publications. But one of the most powerful features of the TOMs is that they can also directly submit requests for observations to many telescope facilities. And as we just heard from Steve, the number of telescope facilities is increasing. And that really helps to, that one. It really helps to streamline the program, and it means you can respond to an alert very effectively, sometimes without even human intervention. So a number of projects have previously developed TOM systems, and they've proven to be extremely useful tools. But to develop one from scratch requires substantial software development effort and expertise. So that tended to mean that historically only very large and well-resourced groups were able to take advantage of them, which is obviously introducing a bias in the community. So the goal of the TOM Toolkit project was to provide an open source and easy to use package that anyone can then use to develop a TOM system for their own science. But we recognize that different science teams have very different requirements. They're trying to do very different goals. So rather than build a single monolithic system or one ring to rule them all, we built a TOM Toolkit package, which provides a functional TOM system right out of the box. But we designed it in such a way that it's easy for the users to customize to whatever you want it to do. So the TOM includes all of the core features, but we include extensive documentation and training materials that will help you to add features, customize the displays, add interfaces to new services, such as your own telescopes, for example, and in particular to add interfaces to your own user-developed analysis software that's specific to your science. Now, the software is already in use by a number of teams running microlensing programs. The example I know best, of course, is the Microlensing Online Platform, or MOP, which was developed by Etienne Bachelet. This was designed to run the Omega Key project at LCO. It is publicly hosted in the AWS cloud system, and that means that all members of the Key project can access the data from around the world. Now, although MOP provides online tools for the team to analyze each event through the browser, it was actually designed to run the entire observing program fully automatically. So when MOP was being developed, we did discover a limitation in several of the alert brokers, which I think is interesting to talk about. Most of them were actually designed with teams that are interested in extragalactic transients, supernovae, gravitational waves, all of that interesting stuff. But microlensing wasn't included as in many of their classification schema. So initially, Etienne had to customize the interfaces to many of the surveys directly and with their own algorithms for detecting events. Now, since that time, the Think broker has now implemented a microlensing alert detection algorithm, which is great. So I'm keen to update our interface to expand our support for the Think broker, but I also think we should push on the other brokers to make sure that microlensing is on the agenda. So having gathered microlensing alert data, MOP then automatically performs modeling of the light curve data for all of the targets at regular intervals using Etienne's modeling code Pylema that we saw demonstrated by Yanni earlier. The resulting parameters are then used to prioritize targets for follow-up observations. And the output of that process is a list not just of targets, but also of the descriptions of the most valuable follow-up observations to make, those that would be then needed to characterize those targets. The observation requests are then submitted automatically to relevant telescope facilities. And the Omega program, of course, makes use of the LCO network, but the TOM package provides interfaces to a range of other facilities as well. Once those observations are carried out, the resulting data products are downloaded and reduced automatically, and the resulting light curves are then immediately uploaded for MOP so that the system can reevaluate each target, and that allows it to respond promptly to any new anomalies or new discoveries that are being made without humans having to be in the loop. So, to show you MOP in action, this is what the interface looks like, and here we can see that the targets have been uploaded or they've been harvested automatically for the various surveys that we are following. And you can see this display is built into the TOM toolkit with the target information table. For the purposes of this demo, I'm going to look at one target in particular, in this case from ZTF. So if you use the search functions on the right-hand side, it will take you directly to the target page for this particular object. And that shows the light curve data that's been acquired to date. Now, MOP is fitting microlensing models to these data automatically, but you can see buttons on the top left side that will also trigger model fitting automatically. And if you change the parameters of the event, you can also run the target prioritization system so that this system will update its observational program. That said, if you want to request additional observations manually, the TOM also provides this interface for doing so. And you can request both spectroscopic and photometric follow-up. Nope, stop. There we go. Now, I mentioned that other teams in microlensing are also using TOMs, so I wanted to highlight the black hole TOM developed by Maja Jablonska and Łukasz Wyzykowski at the University of Warsaw in Poland. This team prefers a more interactive approach where they use the browser-based tools to add and evaluate their targets. So although this system is based on the TOM toolkit, you can see that they've customized it for their team. Now, this team consists of a very large number of contributing observers at many different telescopes situated across Europe, Asia, the US, and beyond. There's an awful lot of people contributing, and they upload all of their observations from all of the sites and share data through the black hole TOM. So if we go now to the targets list, and by pulling down the grouping, you can see that this team includes a wide range of science interests, all of which are managed through the TOM system. They've also added some customized feature like this target table, where you can add parameters according to the survey strategy, and they added a nice order sorting reactive feature as well. And they've also customized the target detail display to display relevant information on the target, but it also provides this microlensing model button, which brings up the modeling tool. And that provides an analysis of whether the event in question is microlensing or not. And that's a great example of how users, their own development tools can be integrated into a TOM system. They've also added a button just underneath the light curve, which allows team members to download data for their own offline analysis. Oops. The TOM toolkit provides tools to receive alerts from a number of Rubin alert brokers, including Antares, Alerce, Laser, Fink, as well as tools for a range of other services such as Scout. Users can define queries using the browser interface, as you can see on the screen, and you can select on various different criteria. The query itself is stored in the TOM so that you can rerun it as needed to get updated information. And then you can add your own parameters and store the target in the TOM. Now you can do that through the browser interface if you prefer, or you can also automate the entire workflow so that the TOM harvests information on targets as they come in programmatically. And you can also add information on targets by uploading a catalog of objects, or gather more information on them by querying online catalogs such as Simbad, NED, or JPL Horizons. In addition to the core toolkit, we've also developed a range of plugin modules with more specialized features designed to support particular use cases. The plugins provide access to additional telescope facilities, such as the Liverpool telescope, as well as providing query functions for Fink and Alerce and other brokers. Now, we've made these plugins optional so that users only need to install those functions that they need for their particular science. And we've structured the package in this way to make it easy as possible to maintain a running TOM system and avoid clashing dependency issues. And we've developed some new plugins which I think are particularly relevant to Rubin and that I'd like to share. Oops. We have a new TOM Alert Streams module that provides an app to listen to Kafka streams, since Kafka is becoming widely used to distribute alerts. These new services include the GCN Classic over Kafka service, as well as, of course, the Rubin alert brokers. And it's straightforward to configure the TOM to listen to any stream that you prefer. We also added a TOM classifications module, thanks to some excellent work by Brendan Mills from UCSB. This different alert brokers are going to provide independent assessments of different alerts. So we figured by comparing the classifications from different brokers, we could build confidence in our identification of targets of interest. Brendan also developed the excellent interactive charts that you can see on the screen so that you can visualize information and synthesize information coming from the different brokers. One aspect that has received a lot of attention recently is the challenge of coordinating follow-up for public alerts when you have many teams around the world all interested in doing the same science. You have duplicated or competing observations are going to be a serious headache for telescope operators, and it can lead to duplicated data. But conversely, if you lack coordination, you can also lead to some interesting targets being overlooked. So real-time sharing of information between teams is very important. And that's a particularly serious problem in the multi-messenger astrophysics community because there's so many people in that community. But microlensing has also run into similar challenges. So I thought it would be interesting to mention some of the tools that we're developing for the multi-messenger astrophysics community. Similar organizations have developed a new Kafka-based messaging system called Hopscotch. This is designed to make it easier to share information through using software, and it's fully integrated with the identity and access management system adopted for LIGO, which is called Keycloak. LCO has developed a portal called Hermes, which is based on Hopscotch. And this portal allows you to post messages with all different kinds of astronomical data, which get converted into JSON and then disseminated via a Kafka stream. And it offers an API, so you can either post messages through the interface on the screen, or you can post them through software like a TOM, and you can then subscribe to information to receive information from other teams and send data of your own. So we have a new TOM plugin which allows the user to select data that they would like to share from this table and to which Kafka topic you would like to post it just by clicking a button. And the new TOM plugin for Hermes supports the IAM system, the identity management system, so that the TOMs can interact very seamlessly and the whole workflow can be automated if that's what you prefer. So to show that very quickly in action, this is a TOM system run by Team 1, and it shows that the data that they have on a particular target. Now, this is the TOM system for Team 2. This is a different TOM, and they don't yet have any data on this object. So if Team 1 then decides that they are happy to share their photometry, they can use this table to select all of the data points and send it to select the Kafka topic they would like to share it with. That then gets sent to Hermes, and we can see the message appearing in the Hermes system, complete with the photometry data. Now, if Team 2 were interested in this object, then they could subscribe to the Hermes Kafka topic, and then they can receive those data just because it will be sent to them via that Kafka topic. And if we reload the photometry page, you can see that the second TOM has received those photometry from Team 1. So teams in the community now have a mechanism for sharing information between groups at the click of a button, even if those teams are using completely different systems. And that should allow teams to better coordinate, especially for rapid evolving events, like multi-messenger gravitational wave events, but also for things like microlensing. And in addition to data sharing via Hermes and Kafka, we're also working on mechanisms that Tom's built with the Tom Toolkit can share data directly. So I hope I've given you a quick overview of the Tom Toolkit and some insight into some of the tools that are already available for microlensing. There's a lot more in our development plan in the near future. We are in the process of making it possible to request observations from a wider range of telescopes, in particular working with the Rubin in-kind process. We're also working with the developers of the Rubin alert brokers to make sure that our interfaces support their services with the latest functionality. And we're working with Desk on a Tom system for their science with some particular features that they need. I'd like to end by saying that we do place a strong emphasis on supporting users of the Tom Toolkit. And in addition to our online documentation, we plan to run workshops at the upcoming AAS meeting for anyone who is interested. And we encourage researchers to contact our team at any time if they need support. So I will end there. Thank you.
Thank you so much. Sounds great. We do have time for one question. Rachel, is there any questions? Natasha?
Hey, this is super awesome. I was wondering, for like versions not of Tom, but like of similar platforms, if we wanted to incorporate like aspects of a Tom where it's like the ingestion of the, say, sets of data like Gaia data, is it relatively easy to integrate aspects of Tom with existing platforms, or do they really need to be built up from the Tom toolkit from the start?
It's certainly easier to build it on the Tom Toolkit because all of these things are back-ended by databases. So it depends on the database structure. But a structure like Hermes is intended to be very general platform. So sending and receiving data in as a Kafka stream or JSONizing it does make it much easier to send information. So I guess it kind of depends on what you had in mind.
Okay, fair enough. Thanks.
Thank you so much. I know a lot of people might have more questions. Please leave your questions on a Slack for Rachel. These are really important topics. So, and we can also discuss them during our hacking sessions, and you can ask Rachel more questions about it. Let's thank Rachel again for this great presentation. Thank you so much. And our next speaker is Martin. And he's going to talk about facilities available in Argentina and Brazil for microlensing science with velocity. Martin, we don't hear you.
Sorry, I wasn't muted. I'm sorry. Yes.
No
Can you
worries.
see my slides? Are they switching?
They're not changing.
Okay, sorry, I'm sharing the wrong window. Sorry.
Oh, okay. I think they're now changing.
Okay, let's try again. Okay, hope it works out. Do you see it switching?
Yes.
Okay, thank you. Thank you. So the idea here is to make a quick presentation on some facilities, mostly observational, but computational too, in Argentina and Brazil that I hope that could be used for microlensing. So the main observational infrastructure for optical astronomy in Argentina is this CASLEO. This is a large astronomical facility in the Andes mountain, which is really close but on the other side of the Andes mountain, as compared to the Vera Rubin Observatory. It's a pretty nice site. It has a large fraction of clear nights. It's not great seeing, but well, that's okay. Its main instrument is this 2.15 meter telescope. It's named Jorge Saade. It has a CD camera, polarimeter. It has two kinds of spectrograph. This is mostly old instrumentation. The instruments, they work well, but it's like, okay, the CCD will be changed for a more efficient one. And actually we have a program to replace the current CCDs with a Rubin-like CCD, in the sense that is a thick, fully depleted, back illuminated CCD, which is sensitive in the red, mostly like the Rubin one. So this is, oops, sorry. So this is something we want to improve. It's partially automated, so it's not like robotic telescope, but we can control it remotely. And it has now a target of opportunity policy. As far as I know, it has never been used for microlensing. There are other small telescopes in the same site, which range from 0.4 to 0.6 centimeters. Some are part of networks, like the Solaris 4 is a network all around the globe, with identical telescopes in, I think, in Africa, Australia, and so on. And there is also a set of smaller telescopes, like 0.4 telescopes. And one of them, I think, was mentioned by Steve. It's part of the in-kind contribution to LSST. There are also a lot, it's like a big site with a lot of people and machine shops. Is like a full institute. In the same place, they are building this China-Argentina radio telescope, which would be the largest single dish radio telescope in the Southern Hemisphere, or sorry, in Latin America. And this is intended to work also on interferometry with ALMA and other infrastructures. But this is at the moment under construction. There are also some other radio facilities. There is an institute near Buenos Aires, the Institute for Radio Astronomy, which has two operating 30-meter dish antennas. And there is also these deep space antennas. I think Steve mentioned one of them. These are large dishes, also 35 meter, and they are used to connect to satellites. But as Argentina gives these companies, ESA, the European Space Agency, and one for China, as it's giving the facilities and in the space, it gets 10% of the time. So the Deep Space Station 3 in Malargüe is also part of the in-kind contribution. This is a picture I have taken 2 weeks ago. I was in Malargüe. This is the vision from a volcano. So this is the Deep Space 3. And there is also a similar antenna southern of that, which is a Chinese one. So, but anyway, I'm not sure this is very useful for microlensing. There is also another observatory called Bosque Alegre. It's even older. It's a 1944. It has a 1.5 meter telescope, which is okay, significant. You see by the green, it's not a lot of clear nights, but still it works. It's also kind of obsolete. So that's the kind of instrument that you have if you can put some time and resources in making it more automated and get perhaps a good chunk of time. It's close to a sort of large city, so it's easy to get, but also the sky is not great. So they are really open to different kinds of collaboration, but they need help. There is also a third site that has been newly explored in Argentina for optical astronomy, which is the Salta province. It's very high altitude, so it's 4,650 meters. It has been a candidate for the extremely large European extremely large telescope. It didn't get selected, but still it's a nice place. It has 93% of clear nights. And one of the instruments that's there, which is the Toros instrument, has already had the first light 2 years ago. It's a small 0.6 robotic telescope, and it's part of the in-kind contribution to LSST. There's a second instrument there that's under construction. That's a 1 meter, mostly near infrared and mid-infrared telescope, which would be like the highest altitude near infrared telescope, it seems. In close to that location, there is the radio telescope called Llama, which is under construction. It's like a copy of one of the ALMA radio telescopes, and it's intended to work in interferometry with ALMA, with APEX, and other telescopes. So with this VLBI, you have you can get a very high precision, 10 times the precision, 10 times the PSF of ALMA, for example. There is another instrument there for CMB, but I don't think this can be used in any means by us. Okay, switching countries, going to Brazil. The largest facility in Brazil, it's basically one main observatory, which is a national laboratory for astrophysics. It's quite new. It was built in the 80s. You see by the picture, it's quite green also, so it's not a great site in terms of clear nights, but it works. It has the main telescope is a 1.6 meter telescope, which was used and it is being used actually for microlensing under the microfun collaboration. It has photometry and spectroscopy. It has also two smaller 0.6 meter telescopes. And this one has been used in the past, like I don't know, 10 years ago for the planet collaboration. And now it's being used for the microfun collaboration. And all these telescopes, they have this classical or remote option to do remote observations, but they are not like fully robotic ones. So about 30 to 40 nights per year of this observatory are being used by Leandro for the follow-up of microlensing events, or even to send alerts. Okay, so Brazil doesn't have a really good site for astronomy, but it participates on this consortium, the SOAR telescope, which is a consortium of basically four institutions, two North American universities, NORI Lab and Brazil. And this is a quite modern telescope. It was built to have a very excellent, very good image quality. So it's kind of Brazil's most important telescope, although it's not in Brazil's soil, but it's a good instrument, and Brazil has significant time on that telescope. I actually, I think I was one of the first users for strong lensing, and I'm still using seldomly this instrument. They have like standard application procedures like all major telescopes. The telescope is in the same ridge as the Gemini and also as the Rubin Observatory, and it has a good pool of instruments. It has the adaptive optics module that corrects for low atmosphere turbulence. It has a multi-purpose spectrograph. It has also a near-infrared spectrograph. It has integral field unit spectrograph, high-resolution camera, and so on. And it's also part of this EON network. It's actually one of the first, I think, infrastructures to be using EON, actually. So this is, I never use under EON, but this is something, I think there are like several programs already, maybe about 10 or more, already working with EON. But as this is, as like a sort of local telescope, if there is something that happens very unusual, like this GRB 221009, which was one of the most bright GRBs ever. Someone was observing. We can talk to these people, say, look, there is this very interesting thing going on. Can I use your time? And so this kind of local is the two extremes, right? We can go through the fully automated EON system, but we can talk to real people and make arrangements if something really great happens. Okay, so I also like to mention this kind of modest computational infrastructure, which is a cluster that I used to manage at Brazil, at the Brazilian Center for Physics Research. It's not a huge, I mean, it's a group scale equipment. It has a very nice node with 128 cores. It has 8 more modest core machines, which have 20 cores. And we have some machines that we call vintage, that are a bit old, but we have 12 of them. So still we have almost 100 cores in these 3 types of machines. We also have a GPU working and quite a lot of storage. So this kind of infrastructure is, of course, it's not like the Buddha supercomputer that we'll hear in a while, but it's like a local infrastructure that has a lot of access. So if anyone in the group is interested in having access, that's something we can provide. Although it's been very, very stable in terms of use. It's connected to the highest internet speed possible in Brazil. So it's really a fully working small scale infrastructure, but it's also very flexible. So if we need to if we need to add a lot of storage, we can do it. If we need to, give more time in the queue for a specific program in microlensing, we can do it. So that's something that I would like to state that's available for everyone. And I hope this can be useful. In a larger scale, there is a group in also at CBPF, which works in the multi-GPU structures. So this is a kind of a hardware development that they do, that they can make these GPUs work together. And so this has been very useful for all kinds of artificial intelligence and machine learning things. They are working to build a machine where the 15 GPUs are connected. So this group has had several awards, both in terms of the hardware, so innovation, but also applications, like in the gravitational lensing finding challenge, which we won thanks to having a lot of GPUs to run these things. They are also running the S+ survey. They do all this transient classification on the S+ survey, which is a 0.8 telescope. And also, this is also the group that's working for Think Broker with the classification, with the elastic data, and so on. Now they are building a really huge world-class infrastructure. We have a lot of funding, like $1 million, which for Brazil is a lot of money. So this is something that they think it really like a world-class GPU infrastructure. They are hiring people. So this is, I don't know if this is possible, but maybe for sure they are interested in maybe discussing an in-kind contribution for SST. So, okay. So just to recap, Argentina and Brazil, they have quite a ecosystem of optical facilities. They are not huge, some are really small, some are more modest, but I think they could be useful for microlensing. Some are already part of the Ruby in-kind program, some need more work, some you just can apply for time and just get this time. So this is something, a question I would like to raise, if we can find it useful for Ruby. And of course, promote integration with the TOM toolkit, with Omega, MOP, and so on. So we are hearing like modern ways of handling small telescopes, and this is not done at all yet here. So I think I'm going to skip to the rest because I'm done with time, I'm sorry. Just say that we have also this time on Gemini that we can share with other partners doing joint progress. Thank you, and I'm sorry to go in above of time.
Thank you so much. Thank you so much. It's really great to know that what are the available facilities. Thanks. We don't have time for any online questions, but if you have any questions, please put them on the Slack channel for Martin, and we can of course discuss them, how we can use these facilities during our hacking sessions. And thank you so much, Martin. Let's all thank Martin again.
I forgot to put my video, sorry.
No worries. And our next speaker is Thomas Love. Thomas Love, are you online? Oh, here you are. Yes, and Thomas Love is going to talk about the supercomputer Bura. Is that how you say it?
Yes, it's Bura.
Bura.
That's correct.
Great.
Yes.
Yeah, thank you so much. And this is also a great facility to use for microlensing work with Ruben. Please go ahead, Thomas Love.
Okay, hello everybody. I hope that you see the presentation. It's in the right display. Okay, so thanks again for the organizers of the workshop that have given me opportunity to present our in-kind contribution. That is mainly the supercomputer. So we are offering computing resources. So I'm coming from Faculty of Physics at University of Rijeka in Croatia. And we are also part of the Croatian participation group, which is an in-kind contribution together with the Institute Ruđer Bošković from Zagreb, from where our program, our contribution leader, Lovro Palaversa is coming. And then also the other partners are Hvar Observatory of the University of Zagreb, and of course, Faculty of Physics. That's the place from where I come. So our in-kind contribution is twofold. One is software development, and it's offered mainly by the Ruđer Bošković Institute and the Hvar Observatory, while we at the University of Rijeka are offering supercomputer Bura as a software processing center. Our in-kind contribution is mainly active in TVS, in transiently variable stars, and also in stars Milky Way and local volume, but we are not reserved only for these two collaborations. We are open also for the others. So whoever wants to use our facility, he's welcome. But these two scientific collaborations, our in-kind contribution were done together with these two scientific collaborations. So they were I would say, I mean, they decided to accept our computing resources for development of the software and for any other use that can be useful for these two collaborations. Then, as you know, there are two kinds of computer resources that are offered through in-kind contribution. One is IDACS, that's International Data Access Center, and the other one is SPC. I will not talk anything about the IDACS because we are not IDAC. We are offering our facility as a software processing center. So we are offering dedicated computer resources, mainly for CPU intensive analysis and for the processing. It's more for the CPU than for the GPU because we are strong in CPU cores and not the GPUs. So that means that this facility is good if your calculations needs a high CPU power, but also a lower disk storage. As I said, we are SPC, we are not IDAC. So IDAC means that they will offer quite a lot of disk storage for their data access, as a data access center. But we are lacking, in fact, on disk storage, but the CPU part is quite strong. So if you think that you need a lot of CPU power, then probably Bura is a good place to be. So as a software processing center, we will contribute with substantial amount of CPU hours. As I said, it will be mainly stellar astrophysics, but we are open also for any other fields of astronomy. For data access, we have a strong cooperation with Slovenian Light IDAC in Maribor. Maybe some of the European contributors have already heard about this supercomputer that is now developing and being put in place in Maribor. It's called Vega. So we will have access to the catalogs and to the LSST data through this facility. Then Bura will be used mainly for the analysis of large amount of data, but also not only for some bulk downloads and bulk analysis. We also want to focus on small scale computing of individual groups that will also give opportunity to smaller groups to use such a facility with a lot of CPU power. I must say that the facility is not suited for development, so there will be no Jupyter notebooks. That means that if you want to use it, you will already you will need to have software already developed, so that you can just deploy it at the facility and use this CPU cores. So no, it's not focused on development. A few properties of the Bura supercomputer. So it's 5 years old supercomputer, so it's not state of the art at the moment anymore, but it was quite good. It was in top 500 high performance computing facilities. As you can see, these are different boards that the supercomputer was on. The maximum power is around 250 teraflops. So, I mean, according to today's standard, it's not really high, but a few years ago it was quite high. And it is still useful if you need a lot of CPU cores. There are altogether 24 cores per node, and there are 288 nodes in the main compute mode of the supercomputer. This is more or less the schematic architecture. What I want to focus more is that there are in fact 3 nodes. One is the compute node with the CPU cores, and then there is an accelerator node with the GPU, and there is also a shared memory or the SMP SMP mode if you need a lot of memory and not so much CPU cores. So these are the three nodes that I was talking about. The first one is cluster node. It has around 7,000 cores, but as you can see, the memory per node is not very large. It's 64 gigabytes per node. But if you need a lot of memory, then it's better to use the SMP node that has around 12 terabytes of total memory that is accessible at any moment by all the cores in the node. But of course, this has only 500 cores, so it's like one order of magnitude smaller than the compute node. And then there is also a GPU node. It has 4 accelerator nodes. It's mainly the NVIDIA Tesla K40 processors, GPU processors. So you can also use this part maybe for some machine learning stuff. The operating system is Red Hat Linux, and for the workload manager, we used Slurm. Data center, this data part and this storage, it's around 1 petabyte, so it's not a large storage. It has a tape library of 2.5 petabytes, but if you need fast access to the data, then probably you will need to use this Scratch file system. On the other hand, for some finished data products and the catalogs, we also have a great collaboration through the regional LSST cooperation grant with the University of Kragujevac, where they now have a nice storage extension, and this was funded by Heising-Simmons Foundation through preparing for astrophysics with the LSST program. I can give just a quick overview of the science cases that we were thinking about to deploy at our facility. One is the so-called dashboard and TVS portal, which is planned to be a data portal for preliminary investigation and analysis of light curves that will be produced by LSST. It's a part of Croatian in-kind contribution, and there is an idea to have a Bura as a backend for more computer-intensive calculations, for example, for statistics, some fitting, periodicity, mining, and so on. Then there is another case with the Serbian in-kind contribution, as they are developing periodicity mining pipeline using also the machine learning. They have a two hybrid code that use different statistical approaches. And we are thinking about using Bura to calculate, to make this periodicity mining on large amount of data. And also to do some cross correlation with other surface. For example, we have already used the IXS software for the cross correlation with the Gaia data. And then the last two science cases is the nonlinear hydrodynamic pulsation models of LPVs. This is planned to be done with the Padova group of Leo Girardi. They are now making simulations of AGB envelope models in order to make synthetic stellar populations, and then they will be able to simulate the LSST stellar content and use it for their mock catalogs, for example, for the three-legal catalogs, so that in the future the AGBs will also be included in much more precise way. Then the last one is the interstellar reddening and determination of stellar parameters by simple main sequence fitting that was already done with the SDSS. Now the same procedure can be used to the LSST, and also there are also plans to make more advanced statistical approach, for example, to use the Bayesian statistics and to try to get not only the reddening, but also the stellar parameters and the distances and so on. And for the last science case, I hope that the microlensing simulations will also be included. We have been already talking with Marcus about this, so I hope that in the future also the working group on microlensing would be able to use the facility. And more or less, that's what I wanted to talk about. And I don't know if there are any questions.
Thank you so much. Thank you so much for the presentation. We don't have time for any online questions, but please make sure that you contact Thomas Love on Slack if you have any questions or if you want to talk to him regarding like running any code or using this facility. And of course, we can discuss that in the hacking sessions for the projects or propose which of them with like this facility would be good for them. Thank you so much. Let's all thank Thomas Love again.
Yeah, thanks. Thanks to you for letting me present the facility.
Sure, yeah. Thank you so much. And so I would love to thank all the speakers. We had a really good time learning about all the projects that have been going on and all the tools and facilities. So we do have like about 20 minutes. So our hope was to be able to go through the proposed ideas. And so the idea is to look at the proposed project ideas and then create some working groups. For example, a working group that is focused on interactions with brokers and what the microlensing subgroup can do with collaborate with the brokers, or one working group that can be focused on the characterization of the events with LSSC. So I'm just suggesting the working groups, but the idea is to look at the proposed project ideas and create these work groups so that people can sign up to different working groups, and this way the like different projects can be conducted in parallel. So for this 20 minutes, I would love to suggest that we go through the project list of project ideas, and everyone who has recommended a project idea maybe can just briefly talk about their ideas, like a 1 minute representation of the idea. And if we don't get to all of the ideas today, it's okay. We will continue on Wednesday. But please also think about like what sort of like working groups we would need to conduct these ideas. And on Wednesday, we will start the working groups. So we will create them, we'll sign up to them, and we will start the actual work in different working groups, defining the tasks and what are the steps to initiate each of those projects. I will share the list of the project ideas. Just a minute, I have to find it. For some reason, Zoom is not able to find.
Yeah, I think I put it in the list if you, or were you trying to share your screen, or are you trying to send the link?
Yeah, I'm trying to find a screen. I have it open, but I can't find it in the Zoom. That's
Here.
I guess just a 2 minutes. Do you
Would you
think
like-
you
I
can
can share
share
my-
it, Natasha? Yeah, that would be great. Thank you so much.
No problem.
Awesome. So if people who have suggested the ideas could just briefly, like 1 minute, speak about their ideas, and then everyone can think of like working groups that are needed, because like some of these ideas have overlaps, and we want to like create working groups in which like 1 or 2 or multiple projects can be included. So Marcus, are you online?
Hi, yes, I'm online.
Oh, great.
Yeah.
Thank you so much for the suggestion. Could you please maybe briefly talk about this?
Yes. So I have been reducing DECAM images of the bulge with Rubin pipeline. So currently I've reduced between 13,000 images per filter in GRI, and the time it covers is from March 2013 to July 2013. And it's around 500 terabyte of data. So the idea is to extend this database to a larger database, which can serve as training set. I have an example of a LiDAR star, which is red points in the left, and red points are from the DECAM images from the Rubin pipeline. And I also have started to use PyTorch DIA to do difference image analysis on the Rubin pipeline produced data from DECAM. And yeah, just try to get more data if it's worth it. Yeah, some ideas and people who can look at the data. The data is public at the Link notebook cloud computing server. So yeah.
Thank you so much. It sounds great. Natasha, could you please? I think Mark is not present right now. So maybe we can move on to the next project and we can just read the whole list on our own again later. Martin, you raised a few questions. Yeah, please go ahead.
So the first, okay, so the first question is connected to the third. So how do we fit in this ecosystem of brokers and so on? So if you want to follow up events, what kind of events we will want to follow up given the large numbers? Who's going to decide that? Who's going to define what the interesting event? Is this science dependent? And also, are us, the Microlensing subgroup, deciding this, or is it the brokers, or we together with the brokers? So that's a bit the question for discussion. The second topic is connected a bit with what Marcus said. He has data on the bulge, which is very interesting to use. Also, Marc Monnier has put something regarding the blending, and Yanis mentioned the simulating data. So I think all these things in a way go in the same direction on how we do the difference imaging, how this affects the flux measurements. And I had a question about that. I mean, this is like something very basic of Rubin. It's something that works for everyone, this difference imaging. So what is the role of the microlensing subgroup? Assessing how it works, giving feedback, doing its own difference image analysis? So that's the question. And I think the last one, I think it's too much generic, is about exotic lens, so not LSST specific. So maybe we can just skip that. I can discuss, of course, if this is interesting to anyone, but for the matter of time, yeah.
Thank you so much. Natasha?
Yeah. So these questions are perhaps my own ignorance, but I think that they should be addressed, is basically how we're going to actually interface with the influx of data. Are we planning to primarily look at alerts from brokers? And in that case, we've discussed that there's been some weaknesses in the past with how the brokers characterize microlensing. So is the plan to use those as a baseline and go off of that? Or should there be some sort of microlensing specific pipeline from the Rubin Science platform? I know there's also occasionally been issues with alerting on longer duration events that, might be longer than the 100 nights of data that come along with the alert from a broker, or you would probably want an alert between seasons or something like this. And so how are we going to deal with that issue?
Thank you so much. Rachel?
The Link Frameworks Incubator Program, there was a deadline coming up for software development proposals. So this was a kind of general purpose notification for everybody, that we have this opportunity to actually get some professional software engineers to develop software with us. Is there anything in microlensing that is kind of ready to go now or in the near future for which it would be interesting to get support brought in to help us develop it? So this wasn't a specific proposal to microlensing, but really to draw everybody's attention to this opportunity, because I think we have we have several software packages that are kind of there, but not quite shovel ready to use. This is an opportunity to bring them to the point where we're ready to go.
Thank you so much. And Yanni?
So there are a lot of really interesting projects already presented, so I'm not sure I should mention that one. But anyway, I would be quite interesting to figure out if there is some software. I know some years ago they were developing a pipeline or to produce or a simulator of Rubin images, what they would look like. I don't know if this is available, but I would like to learn how to use it if such software is available, and basically generate Rubin images, inject stars in them, and then injecting those stars microlensing signals, and then evaluate the signal detection efficiency for different types of microlensing images. This is something that I would be interested in doing. But there's a lot of other, very interesting projects already proposed, and I don't know if anybody actually has used anything like that to generate Rubin images, or if anybody's aware of any type of software that could do that.
Thank you. We should definitely discuss it. I'm sure there are people here who are familiar with it. I can definitely help that with question that project idea. Thank you. Casey Lamb, she's offline, so she's not here, but like her project idea is very related to the work that Marcus is doing with basically looking at the retrieving parameters like TE or parallax. So I think this is definitely something we can pursue. Thank you. And next one, Roseanne. You're muted, Roseanne.
Okay, there we go. Yeah, this was the thing I mentioned earlier that you suggested I put in here. So this is a specific type of thing to look for that we generally haven't considered in the community specifically. And this is when you have a nearby lens, the Einstein angle is fairly large. And in work I did some time ago, it seemed feasible that you would be able to detect events from sources in external galaxies. Now, of course, people have looked at this already with the candidates, say, from M31. But this would be kind of a systematic exploration. Now that we have tentative fields picked out, we know which galaxies are there and also which parts of the galaxies are there. If you're in a really dense area or a diffuse area. Plus, we also know what stars are there from Gaia. What are the nearby stars? So I thought it would be feasible at this point to do a feasibility study and to really see if we are enough events generated and what would they look like, and would we be able to discover them and characterize them. So that may be, this is something we could do independently of the groups, since there are so many great proposals out there. If we don't do it as part of a group, maybe some of us would like to get together and do this in another venue.
Thank you so much. Yeah, it sounds like a cool idea. And we had a few ideas that were proposed at like different weekly meetings. And I'm sorry I didn't write down the names. I did not take notes like the names of the people who proposed them, but these are very interesting ideas, I think. Like, for example, what can we do with early science data? Like preparing a Jupyter notebook for DP0 and microlensing. I think that would be also very useful. Synergies with Roman and Euclid, and having an updated, more accurate estimation of Rubin microlensing yield given the new opsims. So these are the project ideas. So I think the next step is to think of working groups that can basically that can have some general topics, and like if one, two, or like a few of these projects will fit in one working group, people who are interested in that area can sign up and then start working on that. So then I would like to ask all of you, what like working groups do you think would be suitable for these projects? One thing I can think of, there is a definite interest in the LSST pipeline and how the images will be processed and how that would be suitable for microlensing. Roseanne, I can't hear you. You don't seem to be muted. Did you say? I thought you said something. Sorry.
No, I didn't.
So, Marcus, please go ahead.
I think perhaps we can group some of the suggestions into contexts that belong to each other. As you said, the DIAs, image simulation could be one part, but also the galactic modeling, characterization, and simulation is also one big block where we'd need to discuss what we'd like to accomplish. That would involve, for instance, Bora, Tomislav has suggested, or what type of how Popsicle could be integrated. That could be really, because the people are related to that, should be well there for the whole discussion. So I suppose, and that would probably be, well, if those who suggested it could think of a grouping, that would be nice.
Thank you. Are there any suggestions for working groups to create?
So I'd be interested in exploring the DP0, how we can prepare some kind of Jupyter notebook or Jupyter Lab notebook on microlensing, because I know they did something like that for Supernova.
Yeah.
So if we do something like that for microlensing, that would be quite interesting. So I think what we need to do is just go get the Supernova example that they have and try to see if we can follow the procedure to generate a microlensing analysis similar to that one.
Yeah, I totally agree. Yeah. Thank you. Rachel?
So I think it would be interesting if we got together a group of us to work through like an end-to-end analysis of events, because I think Ruben is going to detect an awful lot of different types of microlensing events. It probably can characterize some of those events from some parts of the sky, but it probably won't characterize others. We may need some follow-up. We need to look at exactly what Ruben will be able to measure and what it won't be able to measure. And those things are different in different parts of the sky. For example, for the events that it will detect in the galactic bulge, they'll be heavily blended, but we will be able to use the photometric data to estimate source star parameters, for example. Whereas outside the bulge, we don't have red clump giants, so doing that is much more complex. What I'd like to get to is like an end-to-end idea of how exactly we're going to analyze all of these events and what do we need to do it. Because if there is something that we don't yet have access to, or we don't have the capability to do it at scale, we need to know that now so that we've got time to develop it.
Yeah, that's true. Thank you. Martin?
Sorry, I was muted. Yeah, I don't know, maybe this is already obvious, but I would suggest to have a group discussing this connection with the brokers. Like LSST will, I mean, when we say an event, we are going to model an event. Do we get this information from LSST or from the brokers first? And all connections to this question, right? Selection of events for follow-up, how LSST dialogues with this ecosystem of brokers and these automated schedulers and so on.
Yeah, that's true. That has come up a few times during this meeting. Thank you. Etienne?
Yes, so I will put my Roman hat here. I think a very good potential for both mission with this, the combining data set between Roman and Rubin on microlensing, because actually both mission complement very well. I know some people in this group already think about that, but I think this is an effort that should continue. I'm not sure I will be able to contribute much because time permitted, but I think it's really something that needs to be investigated, and probably we need to define some infrastructure to kind of, cross-match catalogs and stuff like this will be very, very valuable for post-mission actually.
Thank you. I think I did not hear part of what you said. Just want to make sure that I understood it right. So you said combining data from Rubin and what? Sorry.
And Roman W first.
Oh yeah, Roman. Sure. Yeah. Yeah. That. And so by combining the data, like, I mean, what aspect of that you mean? Can you maybe explain a little bit more?
Can you repeat? I'm not sure to understand. Sorry, my colleague have a meeting too.
Yeah, that's yeah, it's a little bit hard to hear your voice. So what aspect of combining the data from Roman Rubin you were talking about? That's what I asked.
Well, I will say just combine the light curve, but same, but not only this, combine sharing the information between the events will be very, very interesting, because there is gaps, for example, in Roman season that will be filled by LSST. So combining this data set is very, very interesting. And I think since there are so big missions that need to be preparing, probably speaking with the agency and all of this. So I think if we can lead an effort on this to show the value of that, that will be beneficial for post mission. But I think Martin and Hannibal already work on this, but I think we should continue our effort on this direction.
Thank you so much. Yeah, definitely. Great. So we're running out of time. Our time is over. But I just want to make sure. Is there any any suggestions anybody want to mention today? All right. So the idea is that we will. I will send this recording to everyone, especially people who are offline, and hopefully we can get feedback from them as well regarding the working groups and project ideas. And so I will write down a summary of that and send it in an email. And please think about the working groups and think about what projects you want to contribute to. And then hopefully on Wednesday, we can summarize the working groups, the projects, and then start working in the working groups. Thank you so much.
Thank you. Bye-bye.
It was really great seeing you.
Thank you.
Thank you.
Thank you for organizing.
Bye. See you on Wednesday.
Bye.
Thank you.
See you.
Bye.